So we're going to start this last unit of the course, inferential statistics, with a few simulations. So what I've done, I'm not going to actually, I'm just going to show you the results, but I've simulated flipping a coin 10 times, calculating the percentage of times it comes up heads, and repeating this process 1,000 times. So the histogram and statistics you're going to see are the results of uh, the percentage of times out of 10 a coin toss came up heads 1,000 times. And if we look at it here, we see that on average, if we averaged all the 1,000 different percentages, uh, it got to 0.024. Not surprising, given the fact that we know that a coin toss is, it's 50-50 to come up heads or tails, right? And we have a standard deviation of 0.163. And as we look at the histogram, we can see that that looks pretty unimodal symmetric. And, we're only flipping the coin 10 times. So the fact that we've got down here on the left, we've got a handful of samples that came up pretty one-sided in either side, either direction, 0.1 or 10% and 90%. Yeah, it's not overly surprising. We're only flipping a coin. We're only flipping it 10 times. So the fact that it came up one head um, some of the times and 9 heads other times is not that outlandish. It's not that common, but it's not that outlandish either. But again, we look at that when we took it when we look at the results of the sampling, all the samples, it kind of mirrored what we would expect to see in any individual coin toss. Now we're going to do the same process. We're going to simulate flipping a coin 100 times, calculating the percentage of times it comes heads, and repeating this process 1,000 times. So this is the result of 1,000 simulations of 100 coin tosses, and we kept track of the heads and tails, or just the heads. Right? Now again, look at that mean, that 0.5004. That's essentially what a coin toss is, 50-50, right? But now look at, as we increase our sample size, look what happens to the standard deviation, or to the spread of the data. It becomes much smaller. We don't have any 10% or 90% heads or tails, because if we did that, if we flipped a coin 100 times and we got 90 heads, something would be up. But again, we see the hints of this unimodal symmetric graph. We got this wonky column in here. That's okay. And then we look here. What if we flipped it 1,000 times and repeated that process 1,000 times? What would happen? Well, that's almost perfectly unimodal symmetric. And again, look at that mean. Look at that. It's centered around that 0.5 mark, but the spread is even smaller still, 0.056, 0.0156. Right? So almost everything, we're really close to within, very, very close to that middle value of 0.4997. Right? So what is this telling us? What are these things? Well, these things are called sampling distributions. And what we want to be doing now, and what we're going to be doing for the remainder of the course, is we want to be looking at and having an idea as to what the behavior of any given statistic over all possible samples of size n. Okay? That's what we're doing when we're looking at what are called sampling distributions. We're looking at, okay, if we went and repeatedly took samples of 10 or 100 or 1,000, and we took many, 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 many different samples, right, what would the distribution look like? This is the histogram that we had up on the screen, right, and where we had a sample of, and it's simulation. It's not what actually happened, but if we simulated 1,000, 1,000, and then 1,000 coin tosses, right? So we um, simulated 1,000 coin tosses and repeated that simulation 1,000 times, right? That's what we would have here. So we've got a pretty good idea as to what the behavior of, in this case, the proportion would look like when we are taking samples of, in this case, 1,000 out of a population with the population statistic of proportion rather of 0.5. This is what it kind of looks like. So what it gives us, what a sampling distribution gives us, is an idea as to how often certain outcomes will occur given the sample size that's being pulled from a particular population, right? And it's going to be a super important tool for what we're doing for the remainder of the course in inferential statistics, right? So, and what we get to say is this, right? And this is what we're kind of seeing indications of, but we're going to talk a little more closely about it, more specifically about it here, right? If we have a reasonably large n value, and we'll talk about that later, a sampling distribution for sample proportions can be modeled with the normal model. That is so important that we can get to the normal model here. And what this indicates right here, this first part here, is right here, mean of p hat, or the mean of the sample means. In all of the three cases that we started with on this lecture, we knew that the probability that any one coin toss comes up heads is 50%. Well, when we went and took 1,000 samples of 10, 1,000 samples of 100, 1,000 samples of 1,000, and figured out, okay, on average, what proportion of those samples came up heads, it was all pretty close to the population proportion of 0.5, right? So we've got the mean of the sampling mean is going to be the same as the population proportion, whatever that is. So if it's known, I didn't mean to almost cross that out, that's going to be our population. That's what we're going to that's going to be the center of our distribution. The standard deviation of our distribution, that's what changed as the sample got bigger. It got less and less spread out. It got more and more compact, and we get to find the standard deviation as long as we know the population proportion. That's a pretty cool thing that we have to do, because we don't always get to do that. We don't always get to base the standard deviation off the mean, but we can when we're talking about proportions. So if we wanted to find the mean of the standard deviation of a sampling distribution for the sample proportions, we're going to take the square root of p times q and divide it by n. Right? So this is all inside the parentheses here. Be careful when you're doing, if you have to do that by hand with the calculator. All right. So when we have a large enough n, we get to model our sampling distribution for the sample proportions with the normal model, and it would look like this. So whatever our population proportion is, that's our mean, and our standard deviation is built from that, which is the square root of p times q divided by n. Right? And we do have, before we can do that, however, we want to make sure we check some assumptions here, assumptions and conditions, and these must be met and spoken to before we can use the normal model. If you're taking the AP test, these are things that they're looking for, right? One, you want to make sure that the sample is independent. Again, we can't always check that, but if it's reasonable to assume that they're independent, that's enough. The sample size n must be large enough. And what that means, when we're talking about that one, go back to our coin toss example, right? We picked sample sizes of 10, 100, and 1,000, right? Well, if we had picked, say we had picked 2. Well, if we had picked a sample size of 2, we would have had 3 options for possible outcomes, right? We would have had 0, 0.5, or 1, right? That's it. We've only had, they either come up none, once, or twice, right? So, um, we can't, that wouldn't be enough to make a graph or make a good histogram, right? So you got to have enough, you know, our sample size has to be big enough. And we'll clarify what big enough is late in future lectures, right? So those are kind of hard to check, but as soon, suffice it to say, if you've got a sample of 20 or 25 or 30, that's big enough. That's probably okay. Um, 10 is probably big enough because as we saw, when we graphed the outcomes for tens, it was point 0.1, point 0.2, point 0.3, point 0.4, and so on and so forth. Well, we had at least 10 columns in our histogram. That's enough. Okay? These we can check. The conditions we can check. Random, right? The samples have to be representative of the population they're drawn from. If you're told it's randomly selected, that's great because that's all you need. You can say, well, we're told the sample was random. We have no reason to believe it's not. If that phrasing isn't included, but based on the context of the problem, the sample that described would it reasonably be expected to be representative, that's fine too. But you got to speak to it. You got to say, we were told the sample was random, so we're going to say that that's enough. Right. The 10% condition. We talked about this one earlier when we were talking about in chapter 17, right? I'm sorry, chapter 16. We can't, if our sample size is bigger, is less than 10%, we're okay. We're not going to affect the independent condition or assumption, right? If our sample's too big, every time, the fact that we draw from it means we're going to affect the likelihood of it, of whatever proportion we're looking at, right? We're going to change it. So our sample size has to be less than 10% of the population. Again, sometimes it's just reasonable to think, but that it's less than 10% of the population. Sometimes, however, you do have to read the problem. You have to say, well, why are they telling us it's a large city that the sample was pulled from? Why are they telling us it's a large university or whatever? Or, if we're talking about applicants to a job, it's however many applicants is probably going to be less than 10% of all the people that could have applied, right? You have to kind of get to that point in the checking the condition. And then it also has to have the success failure condition. Both n times p, our sample size times probability of success, and our sample size times the probability of failure, both has to be greater than 10. All right? So that's just an introduction to what sampling distributions are, right? And they give us the behavior of samples drawn, repeated samples of size, whatever, drawn from a population with a known population proportion. What we're going to do is now look at, all right, in the next lecture, we're going to say, how does that apply to a problem to answer a question? All right? So we're going to get plenty of practice with this because this is the basis, this is the foundation of what we're doing for the rest of the course. So hopefully, if you have questions, please let me know and we will go over them because you got to know this pretty well, okay? That's all for now. Another lecture's coming up soon. Hope this helped, and let me know if you have any questions.